Hello! Welcome to the video lesson of 2.7 Exponent Laws! Putting it all together, where we are going to take a look at all of the exponent laws that we have learned so far, all of the skills we have tackled so far, to help simplify and perhaps even evaluate expressions that involve many exponents. All right, so when we take a look at using those exponent laws, a crucial reminder that we can only use exponent laws with powers that have the same base. So if our powers have different bases, we are not able to do anything with that. We have to simplify in different ways, or that is as simplified as we can get it. So let's take a look at some of the examples. So example 1 is this guy over here. We're going to simplify each expression, and we are going to make sure that our final answers are always stated with the smallest possible base. So if a base can be smaller, we will make it smaller. If it can't, then we will leave it as is. Also notice the instructions say to simplify, so we are not evaluating. It's possible that in some cases we can evaluate. We are just not required to. So we always want to keep in mind what the instructions are so that we know what to do. All right, let's get into it. So for this first example, I have multiplication going on, and I've got some division going on because I have a fraction. Something very crucial to keep in mind is that when we perform these exponent laws simplifications, we are always going to follow BEDMAS. The only exception we will ever make to following BEDMAS is if we have a massive bracket raised to the power of 0, because that is going to be a shortcut, saving us lots of work because we know that value is equal to 1. If we are taking a look at a question like this, we don't have any brackets with a 0 exponent applying to it, so we're not going to take that shortcut. We are going to follow BEDMAS. Now, when we have a fraction like this where we've got lots going on at the top, even though we don't have lots going on at the bottom, there are essentially invisible brackets around the numerator and invisible brackets around that denominator, which means that we are going to tackle this numerator before we tackle the division. So we have to tackle the multiplication before we tackle the division. Must. Okay, and we are showing all of our work. So if we are doing an exponent law, we are showing each line with only one exponent law shown at a time. So for this first step, I'm going to take a look at that numerator. When I multiply exponents with the same base, I add their exponents. Multiply powers with the same base, I add their exponents. So I get 3 to the power of 6. And my denominator stays exactly as is. I have to write it down because my lines should be equal, but it stays the same. Now that my numerator is simplified as possible, and my denominator already was simplified, now I can do my division of powers with the same base. And when I divide powers with the same base, I end up subtracting those exponents. If I'm ever stuck in an exponent law, I could always write it out as repeated multiplication. I don't have to, but it is a way that I can kind of work through things if I ever forget what that law looks like. Now, this is why I said it was crucial to know the difference between simplify and evaluate. If I want to simplify, my end goal is to get here. If I want to evaluate, which I am not asked to do in this question, but I can be asked to do on assessment or down the road. If I want to evaluate, I want my final answer to be a number, not a power, a number. So I would do 3 to the power of 3. 3 times 3 is 9, times 3 is 27. So if my question stated to evaluate, my instruction was to evaluate, then I would say my final answer is 27. So that's the difference in the instructions. Simplify, leave it as a power with the lowest base possible after doing as many exponent laws as I can. Evaluate means to get to that final number answer. All right. Bloop. Example B. All right, when I'm taking a look at example B, I'm following BEDMAS. Anything I can do inside those brackets, I will do first. Unfortunately, there is just nothing I can do. However, I'm looking at those numbers and thinking to myself, geez, I really do not want to multiply 81 and 27, and I need to leave my answer in exponential form with the smallest base. So 81 and 27 just enliven something within me. And I could recognize that those can both be rewritten as powers with a base of 3. 81 can be written as 3 to the 4. And 27 can be written as 3 to the 3. This will then allow me to perform exponent laws with those two powers now that they have the same base. Notice I did nothing else in that line because I'm only doing one step per line. Now that I've done that, now I have a bunch of powers with the same base, and I'm multiplying them, I add my exponents. So the 3 to the 4 and the 3 to the 3, those exponents add to give me 3 to the 7. When I'm taking a look at a squared and a squared, those exponents add to give me a to the 4. And when I'm looking at b cubed and b4, those exponents add to give me b to the 7. Remember, I could only do those. My color coding only shows powers with the same base. I could not do anything by intermingling with those colors. This is in fact my final answer. It is simplified. It is in the smallest possible base. And there's no more exponent laws I can perform. At any point in this video, if you need to re-watch an explanation, feel free to backtrack, re-watch, pause, try things on your own. At this point, hopefully you are able to try things on your own. So pause, do so, and then watch the video to confirm. All right, example C, you've already paused, you've already tried, and now we are here. All right, so now when I'm taking a look at this, even though my fraction is in brackets, I know that there are invisible brackets around the numerator and invisible brackets around the denominator, where I would simplify those both individually before simplifying across that fraction line. Now, there's nothing within those blue sets of brackets that I've added. They're the invisible ones. They were always there, but I've drawn them so we can see them. There's nothing I can reduce within that. But those numbers spark something within me. 64 and 16 can both be written as powers with that same base, and that same base for both of them in the smallest form is 2. Now, some of you might be thinking, well, can't I also write that as 4 to the power of 3 at the top and 4 to the power of 2 at the bottom? And technically your answer is yes. However, that is not with the smallest base. So, it is not the most ideal or most correct answer that we're looking for. So we're always looking to see if we could get the smallest base. If I go ahead and do this, I can still color code within my brackets. So my powers of 2, my powers of x's, and my powers of y's can all be simplified before I deal with that outside exponent. So 2 to the 6 over 2 to the 4, I subtract those exponents and get 2 to the 2. That x in my denominator, remember, if there's no exponent there, secretly has an exponent of 1. So when I divide x squared by x, I just end up with x to the power of a secret 1. And when I have y cubed and divide by y squared, I also subtract those exponents and get y to the power of 1. Now that my brackets have been fully simplified, I can go ahead and deal with that exponent. And when I deal with that exponent, I distribute that exponent to every single power, and I multiply those exponents together, remembering when I have an exponent of 1. So that gives me 2 to the power of 4, 2 times 2 is 4, x to the power of 2, 1 times 2 is 2, and y to the power of 2, because 1 times 2 is still 2. All right, just very, very quickly, if I went an alternate route where I turned the 64 and the 16 into a power of 4 instead, so say I went and said that's 4 cubed, x squared, y cubed over 4 squared, xy squared, all squared, right? My 64 and 16 were turned into powers with the same base, just not the smallest base. I can roll with it, right? When I do that division, I get 4 to the power of 1, x, y. But hopefully at this point, I'm able to recognize that 4 can be written with a smaller base. So hopefully I can take a moment and transfer that 4 into that smaller base now that I'm dealing with a little bit of smaller numbers, which eventually when I distribute end up with the exact same final answer. Now, in the purple is the more ideal work because you're kind of taking the most efficient steps there. But if you did the pink, it's not the end of the world. As long as I see your work and I can follow through things appropriately, I am A-okay. All right. Question D. When I'm taking a look at question D, I'm really liking this color coding thing, so I'm going to roll with it. When I'm taking a look at this, I'm only going with powers that have that same base. If I don't have powers with the same base, I am going to leave them alone exactly where they were before. So no matter what I do in that answer, that n to the power of 8 was in the numerator, it's going to stay there. And that m to the power of 3 was in the denominator, it is going to stay there. Now my l's are to the power of 5 at the top, 2 to the bottom. I subtract those exponents when I divide powers with the same base to give me l to the 3. Now this is as simplified as my final answer gets. There's not a lot of work here. Some of you might be wondering, why is that L to the 3 at the top? And remember that I could always write this as repeated multiplication and then cancel out to become 1s and notice where that L to the 3 should belong. So if you're ever stuck, that's always an option. Okay, we've got 2 more. Oh, we've got 3 more. If you haven't paused the video, pause the video, try it on your own. Last 3, you can do it. And then just touch base when you are done to make sure you're on the right track. I'm going to go a wee bit faster. And in that wee bit, I'm going to maintain my color coding here because I'm really loving this situation. And I've got nothing in my numerator I could simplify, right? Nothing in those invisible brackets at the top, and nothing in my denominator that I can simplify. So now I'm going to simplify across the fraction line. I subtract my exponents when I divide powers with the same base, and I get m to the power of 4 times n to the power of 4. That's as simplified as it gets. For question F, again, I'm going to tackle my numerator first and then my denominator. And with those invisible brackets, I'm going to make sure I follow that. There is this time some stuff that I can simplify in that numerator. And what that is that I can go ahead and distribute that exponent to every single term within my brackets at that top. Doesn't get applied to the denominator because that exponent of 2 only applies to what's immediately next to it, which is that set of black brackets. And those black brackets are only around the numerator. So that's why I'm only applying that exponent to the numerator. When I do so, I multiply my exponents. When I raise a power to a power, I multiply those exponents. So I get t to the 8, r to the 4, s to the 8. And my denominator I did nothing with, so I'm just rewriting it. Just a friendly reminder that this is not an exponent, but this is. Right? Please be very careful on how you express those numbers. If they start looking more like that top, then we're going to start running into some issues. Those are a communication error, but it can also lead to some more drastic calculation errors when you start confusing yourself with your own work. All right, now that we've gone ahead and we've simplified our numerator and our denominator as much as we can, we are going to go ahead and continue on. My division of powers with the same base gets me to subtract those exponents. When I'm looking at s to the power of 8, nothing's happening there, so it's going to stay exactly where it started. It was in the numerator to begin with. It's going to end in the numerator at the end. All right, one last question to wrap things up. We are looking at G. Now, I'm really loving G because I see powers of 10. And as a reminder to myself, powers of 10 are really easy to convert into powers with smaller bases. Right? Powers of 10 can always be written as 10 to the power of something, and that exponent is the number of zeros in that original number. There's 6 zeros here, so I could write it as 10 to the power of 6. I'm going to rewrite all of those big powers of 10 here and not do anything else. The second power of 10 has 4 zeros in the original number, so I'm going to have an exponent of 4. And this is what we've got. So we've simplified just the powers of 10 there, that 1 million and that 10,000, to give me 10 to the 6 and 10 to the 4. Now remember, BEDMAS. BEDMAS says that when I'm doing division and multiplication, I need to make sure that I'm doing it in order from left to right. Of course, I will try and take a look at my brackets first. But if I'm looking at my brackets, there's nothing in there that have the same base that can be further simplified. Which means now I'm dealing with my division before my multiplication. Very crucial, very important. When I divide, usually we've seen division as a fraction, but it doesn't matter what it looks like. When I divide powers with the same base, I subtract their exponents. So when I do that, I get 10 to the power of 6 minus 4, which is 2. A to the power of 8 minus 5, which is 3. And B to the power of 9 minus 5, which is 4. Of course, I still have that times AB squared there. Now, the brackets aren't super necessary because it's just another way to represent multiplication. But I'm doing that next. That's my next step after division, because I always work from left to right if I have interchangeable operations. All right. Now I can use my color coding if I'm starting to really fall for that method. I don't have to, but I can. Nothing's going on with my 10 squared. It's going to stay as is. Do nothing with it. With my A's, remember, I'm now multiplying powers with the same base. I add their exponents. Don't forget that that second A has a secret exponent of 1. And then my B, I have 4 plus 2, which is 6. Nothing can be further simplified. This is my final answer. All right, and that is 2.7. This is combining all of your exponent laws together. Key takeaways. We can only perform exponent laws if my powers have the same base. Second, I can only perform my exponent laws if I'm using BEDMAS appropriately. BEDMAS should always, always, always be followed. If I don't follow BEDMAS, I'm going to end up with some final answer errors, and that's not too great. I also might end up with some exponents or numbers I'm not yet comfortable with, so if I do things out of order, I might end up with some negative exponents, and at this grade level, we're not 100% sure how to deal with those. So, always use BEDMAS for that reason as well. Last but not least, keep in mind that exponent laws only work for multiplying powers with the same base, dividing powers with the same base, or taking powers to a power. Exponent laws do not work for addition and do not work for subtraction. So I cannot apply my exponent laws to addition and subtraction. I would have to do each kind of chunk separately. All right, take a look at that worksheet, give it your best shot, and that is all for now. Bye.